welcome from my side as well. So who is PROTOS? We are a company dedicated to providing modeling tools, software tools, and so on for embedded systems, and provide services around those tools and about software architecture. And who am I? I'm an aerospace engineer. I have developed a lot of different embedded software systems, mainly with focus on architecture, tests, and tools. And yeah, today I'm going to talk about motor control system test. So why do we want to test and why are we doing what we're doing here? So late testing is a real problem. The tests to fix a bug, they increase exponentially with the phase in your project. So what we essentially want and what we do is we bring the integration test and the system test to the desktop of the developer. By doing that, we reduce the cost and we increase the speed massively, the speed of development. So we need to learn and test earlier to fix bugs, for example, very early. So let's have a look at the normal development process of an embedded system. For example, you start on an evaluation board, you configure some drivers, you try them out and so on. Then you program hardware-related software components such as motor controllers, battery control, for example, also bus systems, protocol directly attached to a CAN protocol, and so on. On top of that, you create your software components and you integrate everything to an application. Eventually, you move to the real ECU, so to the real hardware, electronics hardware, and integrate this all to a complete application. So the normal points where most projects test are here. In the early stages, mostly things are only tested with unit tests, if at all. With unit tests, they are very valuable, they are cheap, they are good to automate, but the problem is a thing like a motor control system, you cannot test very good with a unit test because the motor control system has a history, it has states, and so on. So if you do not attach a real motor, it's really hard to run a test. So you need to simulate something for the application to actually work. In the later phases, you can use a hill system test for doing that, also for test automation, and even later in the development phase, you probably want to run a system test, so you get into the car and drive around the block. That's usually very expensive, very late in the process, and the reaction time is very slow. So you do not get a test on every change you make. So most embedded systems are not really tested in those early phases, they are tried out. So what we focus with the mini hill on the early phases of the development. So while you're developing over the complete process, basically, we focus on we call this hardware software integration test. So on the real microcontroller with the complete software stack you're providing, we make a black box test for your application. So that's the basic idea. So what do I really want and need? I want to test what is changed most frequently, and that's your software. The hardware does not change very often, so every couple of weeks or months later, but your software might change 10 times or 100 times a day, depending on your project size. So we want to test every code change of every developer within minutes instead of weeks or even months. So because you need a very, very fast feedback. We want a full regression test also for unrelated code. So why is that? If you have a change in one part of your code and you only try it out in this part of the code, you might have triggered some problems in another part of the code, some side effects. Even in a normal software system, that's a problem. In an embedded system, that's more frequently because you have limited resources, you're using the same memory, and so on and so on. So you might trigger some side effects there. So you want a full regression test to make sure that your system still works after your change. Then a full test automation is a very nice thing to have because you can enforce tests. So you do not get around the test. So every commit is really tested, and you save a lot of time by automating this. And you can do this with continuous integration for a fully integrated and automated test. Then in the end, what you need to do this is an automated hardware in the loop test to test more than pure software units. For example, a motor control system, you need more than just a unit test, or more than even just a test case. So why is it so hard to automate tests for embedded systems? Let's have a look at the motor control system for an oil pump. By the way, it's a safety critical application that's used in offshore platforms, in cranes, in, I don't know, airplanes, and so on and so on. So we needed to test 300 relevant system states for the temperature shutdown, for an error temperature, for example. So how did the customer do this before? They had a climate chamber. They put in the complete system into the climate chamber, including the electronic control unit with the microcontroller, the complete software, power electronics, sensors, and so on. And they even put in the motor, the pump, and the hydraulic system. So the problem with this approach is that it takes ages for a test case to run. The system is relatively slow. And imagine a climate chamber, it takes a couple of hours to go down from 40 degrees plus to 40 degrees minus, for example. And then if you're down at minus 30 degrees, you run out of hydraulic fluid, or the hydraulic system gets stuck because of the temperature. Then you have to open the climate chamber, have to refill the system with hydraulic fluid, and then the temperature's up at 25 degrees again. So that's really hard to automate. And it would have taken around 30 days for the complete test cases to run. It never actually happened. So what we did is we just focused on the microcontroller with the motor control software and the driver. So the complete software stack on the microcontroller. And we simulated the complete environment, including all the motors, all the sensors, and so on and so on. It's not as hard as it sounds to do, but once you have a simulation in place for the complete environment, you can bring the system in any state you want. So by doing that, you can make a failure injection and so on and so on. And you can completely automate the system because it's just a little bit of software with a couple of wires that connect the pins of the microcontroller. It's really good to automate. And we could run all the tests, including all the other tests as well, within 50 minutes for all the relevant states and all the relevant errors. And this runs automatically on every commit. So let's have a look at the different levels and methods of embedded system tests. So let's start with the unit test. The unit test is good to automate, but you can also use a unit test system to test software integration tests, to run software integration tests, to bring a couple of units together. The problem is you cannot test, for example, a motor controller, because you need a motor to be attached to your system if you want to run the tests. So what we do is now we make the smallest possible hardware in the loop test, providing this kind of simulation. And by that, we have a hardware software integration test, including the motor control. The next level would be a hardware in the loop test, so a big hardware in the loop test with sensors, actuators, power electronics, and so on. That's already very expensive and very slow and hard to automate. And the system test usually is really hard to automate. So that's usually not done automatically. So the effort from the unit tests down to the system tests is increasing by orders of magnitude. And it's also really hard to automate a system test, and it's relatively easy to automate a unit test or a hardware software integration test. So now let's have a look at the typical test setup for a motor control system. So on the right side, you have a motor control application. So that's the microcontroller with the complete software stack. On the left side, you have the test system. So the motor controller controls the motor, the test system measures, for example, the PWMs, and simulates the behavior, the closed loop behavior of the motor. So the motor controller can run directly against the simulation. And of course, we have other sensors, other actuators we need to simulate, and bus systems and so on. So instead of the real system, the motor control application controls a completely simulated system, including the motor, plant simulation of a motor. So the simulation enables deep and fast testing, so completely automated tests. And you can also test the unhappy passes, so all the errors by failure injection. If they're only the signals are only simulated, so you can simulate any error you want. That's a very big benefit. Let's have a closer look at such a simulation. So on the right side, again, the motor control. In this case, the motor control generates 3 PWM signals. The plant simulation measures the speed and calculates the frequency of the motor. And according to the frequency of the motor, it simulates, for example, in this case, 3 Hall signals as digital outputs. The motor controller measures them and controls over this closed loop simulation directly the simulated system instead of the real system. So you replace the real motor hardware by a plant simulation and simulate the expected signals. For simpler simulations, you can use open loop simulation, for example, as a playback for sensor input for a simulation. In this case, this kind of motor control, it would be hard to do this with an open loop simulation because they depend on each other, simulation and the plant simulation and the motor controller. So in this case, you usually need a closed loop simulation for a stable control loop. What can you do now with this hardware-software integration test? So the main goal is not to test the motor control itself, but the integration of the motor control with the complete software system, including all the drivers and electric signals. So you can put the system in almost any state you want to test it. And by changing the simulation, you can do failure injection. So this enables the complete automation, thus giving you speed and depth in your test process. As an example, I take again the temperature shutdown for the temperature errors and for the motor. So we look at the microcontroller, including the complete software and drivers, as a black box. So by doing that, I can, for example, stimulate the ADC by providing an analog output for the temperature. So what happens in the system now, that's the black box behavior. In the system, all the signals and so on, they cascade through the system and do whatever they want. But in the end, what I really want to make sure is that we get as an expected effect that the PWM is off after 100 microseconds in this case. So we want to make sure the motor really is off in any situation we have an error. And on the other hand, I want the correct CAN message to inform whoever is interested about the error situation in this motor. So it's a real black box test in this case. So the next 3 slides are about the different kinds of motor control system, just as examples. So the first example is a BLDC motor control, very, very typical motor control for many applications. 3 PWM signals with block commutation. And in the other direction, we have 3 Hall sensors. We simulate them. And the plant model usually runs between 15 and 30 kilohertz. So that's needs to be real hard real time, because if not, the motor controller will not work. So you need a hard real time simulation for that. Then the next example for a typical motor control would be a field-oriented control. In this case, you have again 3 PWMs, and they are measured. And The test system then produces 3 analog outputs. They are merged into possibly into 1, 2, or 3 analog outputs for the motor control system. So you can work with single, double, or triple shunt simulations. A plant model usually runs again with 15 to 30 kilohertz, but the multiplexing for a single shunt needs to be way below 1 microsecond. So this signal, those signals we produce here, they are very, very fast. So we have specialized a method for that. So that's the fastest motor control usually we can control or we can simulate. And the third kind of motor control simulation would be, in this case, a DC motor with a spring reset. So the plant simulation usually is a little bit slower for that. In this case, between 1 and 20 kilohertz. And the position sensor, we simulate this as an analog or a digital signal. In this case, an analog signal for the position, or for the speed, or for the spring force, or whatever it is. And could also be a digital signal over SPI or I2C or something like that. So those are very typical motor control system where you might want to test with an environment simulation. So let's have a look at the hardware we're using to do this simulation. So we want to test the system under test. That's this microcontroller here, in this case a Cortex M4 STM32 on a standard evaluation board. So you don't need specialized hardware to that. If the evaluation board of your microcontroller does not fit on this board here, you put it next to this board and you wire it with those wire jumpers. So those wire jumpers now connect the pins of the microcontroller with the I/O of our test system. For example, digital, analog, SPI, I2C. So all this low-level bus and GPIO you usually have in your system, PWMs, LIN, CAN, and so on. So now we have the I/O connection, signal connection, electrics connection on the electrical level with our system under test, with our test system. So in our test system, you need now 3 things to do. First of all, you need access to the pins of the microcontroller you want to test. So you need to control the I/O. Then on the second level, you need to simulate motors, temperatures, batteries, and so on, because your microcontroller fails immediately, or your application, if no simulations are attached, or if no real hardware is attached. So that's why we simulate all the I/Os. And the third level is, on top of that, now you can build test cases for the happy path and for the unhappy paths. How do we do that? Let's have a look at the software producing now on the system under test. On the system on the test system, sorry, on the test system, we have a model-based development environment to model the structure and behavior for the simulations and for the test models for the test cases. So from those models, we generate C code, we compile it, and we flash it directly to our test system. That's this chip here. And we run it directly on this microcontroller here. So now the microcontroller runs the simulation and the test cases and communicates directly with the system under test. In this case, an Oryx automotive system. We need to run it on the system because we need to be at hard real time. So the simulation and the tests are really hard real time. Then we log, while we are executing the tests, we're logging the tests and we provide diagrams because we transform them into diagrams, because the diagrams are much easier to read for human beings. And in the end, we really want to know what happened if a test fails. So that's why we have a lot of different low-level and high-level diagrams to really provide you with the right information to evaluate what happened in your test execution. And then we we learn and iterate and do the next iteration for your system under test or for your test system. So now, what are the typical response time for the different test levels? Because that's essentially what we want to achieve. We want to achieve a very, very fast test cycle. For a component test, for example, a unit test or software integration test, usually you get a response time of a couple of minutes. So you push the button and after every change and the test runs. That's easy to do, easy to automate. Please continue doing that. Then the next level is the hardware-software integration test. That's normally not done. The next step would be the system test, either a real system test or a hardware-in-the-loop system test. In many cases, that's not run very often because it's so much effort, or the equipment is so expensive that it's used also for other projects. So it's just not free for test automation. So the system test now also runs usually the acceptance tests. That's why the acceptance tests also do not run much more often than the system tests. So now with the mini-hill, we can run the hardware-software integration tests also in the range of minutes instead of weeks or months, because it's completely automated. So on every commit or on every change, you can run the test. So we get a really fast turnaround, and you close the testing gap between the unit test and the system test with completely automated test cases. So the hardware-in-the-loop setup on your desktop looks this way. You have a laptop or your desktop directly attached to our test system, and that's the setup you would use, for example, for one project or one developer. If it gets bigger, the project gets bigger, or you have more developers, or you have distributed development locations, then you need continuous integration, or you can use continuous integration. So every code change is automatically built, tested, and delivered. That's a typical continuous integration setup in your rack. And in this case, we have 8 different projects, hardware-in-the-loop test projects in the same rack here. By the way, I'm sorry for the sound here. They are mowing the grass here behind me. I could not avoid this here. So the good thing about this continuous integration is that you can test every code change of every developer for every project within minutes instead of weeks or months. So every commit is tested. That's what we want to achieve. So the demo setup for a little demo I'm going to doing now is we have on the right side a Cortex M4 controller with 3 PWMs controlling the test system or the motor simulation, the plant simulation, measures the 3 PWMs and provides the 3 Hall signals. Then we have a temperature sensor simulated as an analog output, could also be a digital signal, and a UART to control the speed of the motor control application. So we have a BLDC motor controller here with 3 PWMs and Hall signals. If you have a look at the test cases on an electrical level, you can see the 3 PWMs with block commutation, and on the others, in the other direction, the 3 Hall signals as digital outputs. Then we have the UART to control the speed of the system under test. Here you see another picture of the 3 PWMs and the Hall signals. And so I can show you a little bit better how a test case works on that level. So we have the UART, then we have the simulated motor temperature as an analog value, and we have the model speed also as an analog value to give you a correlation between the test cases. So what does the simulation and the test case think, and what does your system under test actually do? Because it's hard to really evaluate the speed. If you're looking on the PWMs, it's much easier to have a look at the simulated motor control speed that's measured here. So the first test case would be to test the speed change. So we change the speed over UART. Then the PWM in the system under test gets slower, as you can see. The test system simulates the motor, so it's a real closed loop simulation. So also the motor control or the motor simulation gets slower, as you can see here, generating less signals. And here you see the simulated speed. So that's the assumption of the simulator, the motor simulator. Then the next test would be a full stop for a temperature error. So here you see the temperature drops down to error state. And I expect the PWM to shut down immediately and stay off for, let's say, a second or so. Then it recovers. And here we have a limp home functionality. So the temperature is in a warning state, not in an error state. So I expect the system get a little bit slower to cool down, for example. That's a graceful degradation, a limp home functionality, for example. And in the end, I want the system to recover. So I repair the temperature and I go to a good state. And so I want the temperature or the system to recover and the motor control to continue working. So let's now have a look at my demo system. I have here on my desktop, I have my mini hill board. That's this Cortex M4. Those are, for example, the UART cables, RX and TX. Those are PWMs. Here we have the whole signals as digital outputs, and so on and so on. And now we're looking into the software on this side here, on the test system side. So let's have a look at the motor control system. So everything inside this box here is generated, compiled, and is running the test cases and the simulation. So let's start on the lowest level here. We have the adapters for the IOs, so analog, digital adapters, UART. Then we have the duty capture unit with which can capture 3 PWMs. They are measured, they are fed into the motor simulation. The motor simulation runs once for every duty cycle and provides a new speed to the whole generator, which generates the digital outputs. So now what we need is, on that level, we need the simulations. So in this case, the motor temperature, that's really simple. Degrees Celsius in, analog output out. So between 0 and 3.3 or 5 volt analog output. For example, this analog output, that's the analog output 1. That corresponds here to this red cable here. And the motor simulator is a little bit more complex now. So we can use manual C code or generated state machines, or if you have another model like a Simulink model, you can integrate the generated code of the Simulink motor simulation or other motor simulations into this block here. So in this case, I have a state-based motor simulation. I'm opening the behavior. That's a state machine. So I measure the PWM value, and on every change of the PWM value, I memorize the duty and I calculate the new speed. And then I send over the whole generator output. I set the new speed in the whole generator, and the whole generator now generates the signals according to this new speed. I could change the speed, I could change the direction, or whatever I want to do. I could break a cable, one of the 3 phases, or whatever I want to do to create a fault, to inject a fault. So that's relatively easy to do now because it's just a simulation. So now the third thing I need is the test case. So here is the test case. The test case either directly connects with the system under test over UART or the temperature simulation, or connects with the motor simulation, because it's relatively hard. It's really hard to detect problems just based on PWM, but that's why I have the motor simulation here. The motor simulation already knows the speed. So if I change the speed over UART, the motor simulation is running against the control, the motor control, and knows the speed anyway. So I ask my motor simulation whether the motor works correctly or not. So, and now the test case is could also be a state machine, but in this case it's not. We have a much more efficient way to model state machine. It's just a different behavior. So it's not manual C code. It's not a state machine. It's a test case. That's a test language that also integrates deeply with my test system. So for example, let's have a look at the lowest level steps. Let's request a new speed. So that's a step that requests a new speed. We send a UART command with the speed request to the system under test, and we expect a reply that the speed was set to a certain value. So that's already the UART reply of the system under test. And in the next step, I want to check the speed. So what I'm doing to check the speed is I ask the motor simulation to give me the current speed. And it replies, and I can check whether the actual speed of the system is in the right range. So you see on the right side, you see we always render diagrams, sequence diagrams for every step. For a single step, that's not so hard to do. But if you have a sequence where you combine several steps or several other sequences into a test case, then here in this case, for example, you can see the complete test case, including all the steps. And on the top level, you have a test suite, for example, for all the motor functionalities, and you see the complete specification for this test run. So that's the specification. Now we can generate the code and compile the code and run the test on the system against the system under test. So I'm going to show you now how we do this. We trigger this manually. So you have the graphical user interface. I connect with the test system. So that's the test system. That's the system under test. And now I can start the test cases. And while I'm running the test cases, I'm pulling the plug, and I'm producing an error by doing this. So this should produce some error. Now I'm repairing the system again. Now you see system's working again. And now if I want to see exactly what happened in my system, I can look at this sequence diagram. Now that's not the specification anymore. That's the real log for the real test run. So I'm clicking on the timeout, so the first place where it actually failed. And now in my development environment, I see the exact position where the test failed. So activate motor control, that was exactly the position, just a second, where it actually failed. Yeah, activate motor control. So that's how we do that. So now that's how you do it on your desktop. You just compile your application, you flash it to your system under test, you push the button, and you run your system test or your integration test. But if you want a complete automation, I have a Jenkins server here locally running, continuous integration server. Now I'm going to change the real system under test. Now we are on the right side, on the system under test side. And I'm doing a little sabotage here. I'm changing the duty cycle always to 20%. This should trigger some kind of problem, I guess. So now I'm going to commit the change. Wherever I'm sitting, I'm committing the change to the Git repository. I'm committing it, and while I'm waiting here, you can see already that the continuous integration server will be triggered. So that's what you see here. On the other side, I have we have a look at the system here. Now we check out automatically the new software. We assemble system under test and test system, and then we flash both to the real hardware. So now you will see that the system under test stops blinking, on the test system stops blinking because it's flashing you. Here you see it stops blinking, and because it's flashing you, so that's the test system. And now the system under test is flashed. It also stopped blinking. And when both are flashed, now the tests are running. So I'm going back here and have a look at the test log, and now it failed. So why did it fail? Because I made an error. I'm still connected to the system under test from my graphical user interface. So let's rerun this. And that's usually something you do not have to do manually, because on a continuous integration server, you have not you don't have a graphical user interface. So same thing again. So now we run the tests again, and it's flashed now. And in the end, I expect to throw an error. So in this case, it could not flash the system because I've still been connected or run the tests. And now the tests are running. You see the command line log, but that's not so interesting, because in the end, what we want is the result here. So I see that there's a result here. It's yellow. So let's have a look at the last test results. You can see that the motor integration test, limit temperature, test motor control speed, they all failed. So now let's have a look at why they failed. So the demo integration test failed. Let's have a look at the loggings. So the motor demo state transition tests, no, the integration tests, that's where it failed. And now let's have a look at the test case that failed. I'm clicking on the test case. And now here in the development environment, you see where the system failed. So it failed because it got the wrong actual speed, which is clear because I changed the PWM to 20% statically. So of course I produced an error. So that's the closest you can get to really knowing what happened in your system. So that was the demo. I hope you enjoyed the demo, and if you have any further questions, don't hesitate to connect to Michael Weiss or to myself. We are there to answer your questions. Thanks for your attention.